I'm Manju from Northwestern University. Today, I'm going to do a presentation about our deep learning project on face mask recognition. In the last 2 years, with the spread of the COVID-19, people must wear masks. In many cases, we need to perform mask identification. Traditional labor-based supervision system will cause a great waste of labor resource. Thanks to advances in computer science and artificial intelligence in recent years, we can use image-based deep learning techniques to solve this problem. That is, collecting facial images through cameras and performing mask-wearing recognition with specific deep learning frameworks. In this way, labor and time costs can be saved, and the spread of COVID-19 will be more effectively controlled. In this project, we use face mask recognition dataset. It has 3 classes: correct masking, incorrect masking, and no masking. Each class has around 1,500 images, and the dataset has around 4,500 images in total. We use 4 methods of deep neural network, and we try to use GAN to get larger dataset. Then let's turn to Jiaqi's part to talk about GAN.
Getting large dataset is one of the most reliable ways to improve the performance of machine learning algorithm. In some cases, adding generated or synthesized data can also improve the performance. The generative adversary network can generate synthetic data for a given random noise vector, so that to further improve the performance of our model, we will use the generative adversary network to generate the people masking images. So, however, our generator couldn't learn enough image feature from the limited target dataset to generate accurate and beautiful images. So to solve this problem, we employ this idea of transfer learning. First, we use the sellable dataset to pre-train the network and get the initial base model. And later, we use the no masking images in the target dataset to train the model for the second time. And here, in order to avoid the loss value of the discriminator becomes 0, we only use the pre-trained generator model and discard the discriminator model. Finally, we train the network with the entire target dataset and get the result, which is satisfactory.
Then we use several convolutional neural network models to do the classification task. The first model we use is AlexNet. AlexNet is the first deep convolutional neural network model. It was proposed in 2012 and contains 8 layers with 5 convolutional layers and 3 fully connected layers. It uses the ReLU activation function. After some convolutional layers, some will have the max pooling layers. The second model is VGG16. It was proposed in 2014 and is a pretty large model at that time. It contains 13 convolutional layers and 3 fully connected layers. And the third model is the ResNet18, the residual neural network. It is a very deep neural network. It can solve the degradation problem by utilizing the skip connections to jump over layers. And the last model is EfficientNet. It was proposed in 2018. It is a scaling method and can transfer very well.
In order to achieve a higher accuracy, we also try a pre-trained ResNet18, which has been trained on a large dataset. We then use transfer learning to reuse the trained weights of this pre-trained model on our datasets. Here shows our results of accuracy and confusion metrics. We can see the pre-trained ResNet achieved the highest accuracy, and the true positive rate of wrong mask is less than the other 2 classes for most of our models. This means the images of wrong mask is harder for our models to classification. Finally, is our conclusion and future direction. First, using transfer learning to reuse features learned by the pre-trained GAN model largely help us to gain a powerful model which can generate images similar to our face mask datasets. This also proves that GAN can be used as a powerful data augmentation technique. All our used CNN-based models achieve accuracy over 19%. Some of them even achieve accuracy of 97%. We can conclude that CNN is a very suitable and powerful features extractor and predictor for images. In the future work, we can reduce the original data size to train these CNN-based models, but introduce images generated by GAN for training. This can simulate the real situation when original data is not sufficient, and see if GAN can help improve model ability. That's all of our projects. Thank you for your attention.